In section 2.5, we introduce the concept of a function. So first we need to define what it means to be a relation. And so the definition of a relation is that it is simply a set of ordered pairs. So look at these ordered pairs we have here. We have 3, 5, -4, 2, 0, 1, -5, 8, and 3, 2. And this relation gives a correspondence between two variables. We have a variable in the first spot, which we usually call x, and a variable in the second spot, which we usually call y. And technically we call the first one the first coordinate, and the second one the second coordinate. Also, you can use the word component instead of coordinate. But what you have here is a relationship between these two numbers. So think in terms of x and y for a moment. This says when x is 3, y is 5. And we can actually draw that down here as a graph. We can say that the x-coordinate of 3 corresponds to the y-coordinate of 5. And so let me go ahead and draw an arrow from 3 to 5. The second point says that x equals -4 corresponds to y equals 2. And we can draw a line for that one as well. X equals 0 corresponds to 1. Let's go ahead and show that. And -5 corresponds to 8. And so let's show that one. So far it's a real nice correspondence. And then for our last one here, it says 3 corresponds to 2, which is interesting because the first point here, this first ordered pair, said that 3 corresponded to 5. I'm going to draw that in a different color just so you can see it a little bit better. But if 3 corresponds to 2, then it looks something like this. And this is a little bit problematic. It's problematic because we have an x value of 3, and it corresponds to 2 different y values. And this is not well defined, because if I tell you that x is 3, you would want y to be uniquely determined. So although a relation can be useful for some things, we certainly don't like relations where this occurs, where one first coordinate goes to 2 separate second coordinates. So let's introduce the concept of a function. So a function is a set of ordered pairs, which is the same thing as a relation, in which to each first component there corresponds exactly one second component. And those are the key words. You get exactly one, not more than one. So let's take a look at this set of ordered pairs, and let's draw a function map. So 3 gets mapped to 2, 4 goes to 5, 6 goes to -1, and 0 goes to 5. See, this is a function, and I know you might be a little bit confused because you have 2 ordered pairs that have different x values going to the same y value, but that is actually okay. It's well defined. What we need to know is where does each point go? Each point over here in the first component has to only go to one point in the second component. So it's okay that 2 different numbers here go to the same number. What you can't have happen is what happened on the previous page, where one value of x was going to 2 different values of y. Now the set of all the numbers in the first component slot, and so that would be 3, 4, -6, and 0. Those numbers make up what we call the domain. And the numbers in the second component spot, which would be 2, 5, and -1, those make up what we call the range. And so when you hear domain, you should be thinking these are the x values, and when you hear range, you should be thinking that these are the y values. We can also describe functions using an equation. And so I have a couple examples here for you, and I'd like to know, does the equation y equals 2x minus 5 represent a function? Is this a function? And if so, why? Or why not? So what you have to do is you have to imagine if you start plugging in values of x here, are you ever going to plug in one value of x and get two values for y? Let's experiment a little bit. If x equals 3, y is going to be 2 times 3 minus 5, which is equal to 1. So when x is 3, y is 1. So when we plug in 3, we only get one value for y. What if x is 0? If x is 0, y will be 2 times 0 minus 5, which is -5. And so that gives us the point 0, -5. Again, one value for x produced one value for y. And you get the idea that if we keep picking values for x, so here's another one, x equals 4. If we keep doing this, we're going to keep getting only one value for y. Now, this is not a proof that it is a function, but it's suggestive that it is a function. If you graph these points, we know that this graph is going to be a line because we have some experience graphing lines. And so let's go ahead and just sketch a real quick graph. And this won't be a very nice graph, but it'll get the job done. We have the point x equals 3, y equals 1, x equals 0, y equals -5, and x equals 4, y equals 3. And you can see that those 3 points make that line. Now what's important here is if you imagine drawing vertical lines here, every vertical line that you can draw to this graph is only going to hit the graph one time. What that means is that when you pick a value for x, there is only going to be one y value associated with that value of x. So imagining drawing vertical lines, and I'll do this in red here so you can see it, notice that every possible vertical line that we draw only hits the graph one time. If that is the case, then it is a function. And this is the vertical line test. And what we notice is that all vertical lines intersect the graph only once. If it intersects the graph more than once, then you do not have a function. So, long story short, yes, this is a function. Okay, next one. The equation y squared equals x plus 1 is not a function. Why? Why is it not a function? Well, let's see what happens. If we choose x equals 3, what is y going to be? Well, y squared will be 3 plus 1. And that means y squared will be equal to 4. But if y squared is equal to 4, we know that y can be 2 or y can be -2. Because 2 squared is 4, and also -2 squared is 4. This is a problem. what we have here is a single value for x, and we're getting two different values for y. Now, I'll spare you a lot of the details here, but if you graph this equation, here's what you get. So here's what the graph of this equation looks like. Now, I didn't show you how I got these points, but basically, if you plug in some additional values for x, you can find some additional points on this graph. Notice that the graph goes sideways like this, and in particular, notice that if you draw a vertical line here, you will hit the graph more than once. If you hit the graph more than once when you draw a vertical line, that means the graph does not represent a function. So, this is not a function. So to say things a little bit differently, we say that y is a function of x if you are given a relation in x and y, and each value of x in the domain corresponds to exactly one value of y in the range. If this is true, then y is said to be a function of x. So this is just another way to think about the wording of what it means to be a function. Now let's talk about function notation. Function notation is a special notation that we use when we're dealing with a function. So let's consider the equation y equals 2x minus 5, which is a function. Function notation is when we replace the variable y with the notation f of x. And so I want to point out, first of all, that in this notation right here, f parentheses x parentheses is pronounced f of x. That's how we say it. So down here, y equals 2x minus 5 is a function, and therefore we can rename it f of x equals 2x minus 5. So notice that f of x is just replacing the variable y. This is special notation that we use for functions only. And it turns out that it's very convenient. Let me show you an example. In this example, we actually have three functions. We have the function f of x, which I am defining to be negative 3x plus 2. We have the function g of x, which is defined to be x squared minus 5x. And we have the function h of x, which is 3 divided by x plus 1. So what's nice about function notation is that it literally gives each function its own name. The name of the first function is f. The name of the second function is g. And the name of the third function is h. And so down here, if I say, find f of negative 4, think about what you're being asked to do there. F of negative 4 quite literally means that you're replacing x with negative 4. So the number in here is the input value. It's the x value. Well, if you plug that into the function f of x, you get negative 3 times negative 4 plus 2. This is equal to positive 12 plus 2, which is 14. So f of negative 4 is equal to 14. This is really convenient notation because negative 4 represents the x value and 14 represents the y value when x equals negative 4. How about part B? Part B is asking us to do g of 4. G of 4 means to go to the g function and replace x with 4. And so if we do that, g of 4 is going to equal 4 squared minus 5 times 4. So please understand what I'm doing is I'm taking x equals 4 and I'm plugging it into here and to here. And if we do the math on this, we get 16 minus 20, which is negative 4. So g of 4 is equal to negative 4. So on the function g, when x equals 4, y equals negative 4. Let's try another one with the function g. Part C says find g of negative 3. G of negative 3 is exactly the same as what we did in the previous example. We're going to replace x with negative 3. Now when you replace x with a negative, if that value is negative, you need to make sure you use parentheses every time you do it. Now, anytime you substitute, it's a good practice to use parentheses, but it's particularly important when you have negatives. So, negative 3 to the second power, what is that? So let's remind ourselves that this means negative 3 times negative 3. So that would be equal to 9. And then we have negative 5 times negative 3. That is positive 15. And so we end up getting 9 plus 15, which is 24. So g of negative 3 is 24. So again, negative 3 is the x value, and 24 is the y value when x equals negative 3. And for our final example here, we are trying to find h of negative 6. Well, how do we do h of negative 6? We have to go to the h function, which is right here. And we are going to substitute x equals negative 6. And when we do that, we get 3 divided by negative 6 plus 1, which is 3 divided by negative 5, which we can rewrite as negative 3/5. You could also give a decimal answer here, but fraction answers most of the time are good enough. So h of negative 6 is negative 3/5. And again, x's negative 6 produces a y value of negative 3/5. So function notation is very practical because if you're talking about more than one function at the same time, you can give each function its own name. For our next example, let's consider the function f of x equals 2x minus 5, and let's graph f of x. So to graph a function, all we need to do is get some ordered pairs. So for this, I'm going to pick some values for x, and those values of x will produce values of f of x, which are also our y values. Now you should recognize that this is a linear function, if you look at it, because you should notice that it has the format f of x equals mx plus b. M is the slope, and b is the y-intercept. So we know that this graph is going to be a line. Let's plug in some numbers. Let's plug in x equals 3, x equals 0, and x equals negative 1. Now when x equals 3, f of 3 will be 2 times 3 minus 5, which is 1. If x is 0, f of 0 will be 2 times 0 minus 5, which is negative 5. And when x is negative 1, f of negative 1 is 2 times negative 1 minus 5, which is negative 2 minus 5, or negative 7. And since we know that this graph is a line, this is enough points to sketch the graph. So let's go ahead and import the graph in here now. So here's the graph, and let's just double check that it all makes sense. So we found 3 points, and those 3 points are in this table, and they are 3, 1, 0, -5, and -1, -7. So 3, 1 is here, 0, -5 is here, and -1, -7 is here. So we can verify that those 3 points do make this line. One more concept as it relates to functions and their graphs is that if we're given the graph of some function, so here is the graph of f of x, we can answer questions about it by using the graph. So using the graph here, what is f of -1? What are you being asked to do here? Remember, the number on the inside is the x value. So x equals -1 is right here. So this is asking, what is the y value when x is -1? So we can use the graph to figure out that the y value is actually equal to 4 when x equals -1. So we can say f of -1 is equal to 4 by just looking at the graph. So in part B, what is f of -3? Again, -3 is the x value, and you can see the graph crosses the y-axis right there. So that means the y value at -3 is 0. And finally, we can do it the other way around. For what value of x does f of x equal 3? See, now you're being told that the y value is 3. If the y value is 3, what is the x value associated with that? So to do that, what I'm going to do is go to the y-axis, and I'm going to find out where y equals 3, which is right here. And notice that the graph actually has 2 locations where y equals 3. And so what is the value of x that corresponds to y equals 3? All we have to do is drop down to the x-axis, and we can see that one value is -2, and the other value is 0. So for what x value does f of x equal 3? Well, x equals -2, or x equals 0. It's actually 2 values. All right, moving on to section 2.6, we're going to look at graphs of functions in a slightly different light. So I want to share with you the graphs of 3 important functions. These are basic functions. One is your square function, which is f of x equals x squared. And this is what that graph looks like. It's also called a parabola. And we will talk more about parabolas later in the course. Next, we have our absolute value function. F of x equals the absolute value of x. And this one gives you sort of a V-shaped function. And it's not difficult to graph. You would just plug in values of x, find values of y, and sketch the graph. And then finally, we have our cube function. F of x equals x cubed. And this is sort of what most students call sort of an S-shaped graph. Now again, any of these graphs you could do by just getting some values. And so let me just share with you for this middle one here, the graph of f of x equals the absolute value of x. If you've never graphed this before, you can pick values of x and find values of y. And so if I pick x equals -2, 0, and 3, for example, the value of y is we're just going to take these values of x and plug them into the function. So when you put -2 in here, you get the absolute value of -2, which is +2. When you plug 0 in here, you get the absolute value of 0, which is 0. And when you plug 3 in here, you get the absolute value of 3, which is 3. And if you graph these points, x equals -2, y equals +2 is this point, 0, 0 is this point, and 3, 3 is this point. And so you can see how it makes this sort of V-shaped graph. Okay, so these are just 3 basic graphs that I would like for you to memorize. They're important graphs in algebra. What we want to do now is we want to use these graphs to graph what are called transformations of these graphs. So let's just look at the graph f of x equals x squared, which is our parabola graph. If we know f of x equals x squared looks like this, what do you think f of x equals x squared minus 2 is going to look like? What does the -2 do to the graph? Well, think about it. If you plug in a value of x, let's say you plug in x equals 3. 3 squared is 9. When you subtract 2, 9 becomes 7. So you're decreasing the y value by 2. So graphing something like x squared minus 2 is going to shift the graph down 2 units. So instead of x squared being here, x squared minus 2 will come down here. It will shift downward 2 units. So if that's the case, then what do you think happens to x squared plus 3? Well, if x squared minus 2 shifts the graph down 2 units, then x squared plus 3 should shift the graph up 3 units. Let's bring the graphs in to show you what I'm talking about. So here they are. The first graph, f of x equals x squared minus 2, is represented by this graph. And what you should notice is that this graph has the same shape as x squared, but it is now down 2 units. The vertex of this parabola here, the lowest point, is at -2 instead of 0. X squared plus 3 is this graph, and you can see that it crosses the y-axis at +3 instead of 0. So, again, this is the graph f of x equals x squared plus 3, and this is the graph f of x equals x squared minus 2. So adding or subtracting something to the end of a function moves the function up or down that many units. So what do you think will happen if we take our function x squared and we add or subtract something to x on the inside before we square it? What do you think will happen? Well, if adding or subtracting outside the function moves it up and down, then one might suspect that adding or subtracting on the inside of the function would move it left or right. And that is, in fact, the case. So what does your intuition tell you? X plus 3 is going to move it what? 3 units to the left or 3 units to the right? Let's bring in the graph. Okay, so here it is. So what happened? X plus 3, quantity squared, this is our blue function. That's represented by this blue graph. Notice that it has been shifted 3 units to the left. Now, why does it move to the left? Because if x equals -3, -3 plus 3 is 0. And so that's going to be your vertex point. For the other function, the red function, f of x equals x minus 4 squared, that one moves the graph 4 units to the right. Why does it move it to the right? Because if x is positive 4, 4 minus 4 is 0. And so that vertex gets moved 4 units to the right. So the bottom line is, when you add or subtract something to a function, either on the inside or on the outside, that's going to move the function up, down, left, or right. And I'm going to summarize this on the next page. So in general, if you have a graph of f of x, if you know what f of x looks like, and if we assume that h and k are positive numbers, then the graph of f of x plus h will shift f of x h units left. F of x minus h will shift f of x h units to the right. Okay, so this summary right here is what happened here. F of x plus k will shift f of x k units up, and f of x minus k will shift f of x k units down. This is what happened here. And finally, one that we have not had an example of yet, if you put a negative in front of your function, that reflects the function over the x-axis. So for example, for that one, let me give you a quick example. You know that y equals x squared is a basic parabola. So y equals negative x squared is just going to take this graph and flip it over the x-axis. So negative x squared will look like this. That is what we mean when we say it reflects f of x over the x-axis. Let's do one final example. So for this one, we're going to use the knowledge of the graph of f of x equals the absolute value of x. We talked about this. This is our V-shaped graph. And what we want to do is graph the function f of x equals negative x absolute value of x plus 3 minus 2. So we have a horizontal shift, 3 units to the left. We have a negative, which does a reflection over the x-axis. And we have minus 2, which shifts the graph down 2 units. Some people can handle graphing that entire new graph in one step. What I'm going to do is take it slow, take it step by step. So first, we're going to ask, what would the graph of f of x equals the absolute value of x plus 3 look like? Given absolute value of x looks like this. What does x plus 3 do? This is on the inside of the absolute value. When it's on the inside, it shifts it either left or right. And when it's x plus 3, it's going to get shifted to the left 3 units. So let's bring in the graph to show what just that would look like. So there it is. There's that same V-shaped graph, but it has been shifted 3 units to the left. Now, why did I do that one first? Well, because the plus 3 is the closest thing to the x, so that's what I choose to look at first. Now that we know that this graph looks like this, let's go to the next step. Let's put the negative in front now. What does negative absolute value of x plus 3 look like? Well, the negative is going to take our previous graph, this graph, and it's going to flip it over the x-axis. It's going to reflect it down here. Let's bring in that graph. So here it is. We've taken this graph and we've reflected it over the x-axis. So it still is at -3 here, but now it is reflected over. The final step now is we need to bring in the -2. So we're going to take this last graph and we're going to subtract 2 from it. Here it is. Subtracting 2 will take our most recent graph here, and that will drop it down 2 units. And so the graph should be right in here. Let's bring in that picture. So here's what the final graph looks like. Notice that we took the original graph, shifted it 3 units to the left, which gave us this graph, reflected it over the x-axis, which gives us this graph, and then finally moved it down 2 units, which gives us this final graph here. So this is called graphing by translations and reflections. Notice that what I'm not doing is I'm not plugging in points for x. You can always do that, but this is a slightly more sophisticated way to graph some functions. Okay, so that concludes 2.5 and 2.6.